Why are you waving at people like you're creating the population? Both greeting for people. Yeah. No matter getting. I would definitely. I feel like you're gonna be like. Hey, no way that. That's the first time. I don't think climate change. That's crazy.
All right, does everyone have the quiz review worksheet packet?
Is it this one?
Yes. Okay, so let's go ahead and try number one. Number one says apply mean value theorem to find when the instantaneous rate of change will equal the average rate of change on the interval from 1 to 3. So remember, there are two conditions for mean value theorem. What are they? The function has to be what? It's continuous on the closed and what? Differential on the open. Okay. So we want to make sure we write out those statements.
You just raise back.
Yeah. So after you, yes. You get one. Next up, instantaneous rate of change. You know that is referring to a derivative component equal the average rate of change. That's going to be your average slope between the endpoints. My suggestion is go ahead and find your average slope first. So stay away from the derivative until you've figured out this number. That way you don't accidentally start plugging numbers into the wrong function to build your average rate of change. So find your endpoints. So find the y value at 1, find the y value at 3. Go ahead and figure out what that average rate of change is. And then yes, you can use your calculator on this quiz. And the big picture of what we're doing here is whatever the graph looks like, we're going to be able to find the average, the slope between the two endpoints. And then we're going to figure out through this process, where else on the graph is there a guaranteed slope that we're looking for here? Okay, so my order pairs are 1, 5, and 3, -3. The average rate of change is just -4. That's the slope between those two endpoints. So now we have this component of our mean value theorem. So now we're asking, okay, we know what slope we're targeting. We're trying to figure out where on the curve is the graph going to experience an exact steepness of -4. And this is where we're going to rely on the derivative. And then we're going to, once you have the derivative function, remember the derivative can work in either way here. You can either give it location and ask for the slope, but you can also give it the slope and ask for the location. And that's what we're doing here. We know what slope we want. We're more concerned about, can we locate that physical place on the graph? So -4 plugs in for y prime. We can work backwards there, solve for x. When we solve for x, we get 2. So that 2 tells us that at 2 on the curve, that graph is experiencing a steepness of -4. Yeah, good question. With extreme value theorem, with mean value theorem and extreme value theorem, there is no explanation statements required. It's really just the work. Yeah, the explanation statements that we really had to worry about was intermediate value theorem. We had to go through all those messy wordings, but with EVT and with mean value theorem, it's really just the work that is your justification. Right, everybody okay with number 1? Number 2, what is the absolute maximum value and the absolute minimum value? So we're looking for absolute max, absolute min. This is the extreme value theorem process. So extreme value theorem requires continuity on the closed interval, but no statements of differentiability. Okay, so we don't need the graph to be a smooth curve. We just need the graph to be connected. So no statements of differentiability for extreme value theorem. We only do differentiable for mean value theorem and Rolle's theorem. And our strategy for extreme value theorem is, once we establish the function is continuous on the closed interval, we're going to find the critical points from f prime. Right. If there's a denominator of f prime, then we have to look in that location as well. But if there's no denominator, then it's just going to be your derivative. Set the derivative equal to 0. Make sure you have valid critical points, and then you want to test valid critical points and endpoints back into the original function and compare the y values. Highest y value is your absolute max, lowest is your absolute min. What I mean by valid critical points is it needs to be a critical point that sits between the endpoints. Okay. If you're working ahead of me, you guys have the key attached to your packet. You can check your answer there. This is yesterday. Okay, so in this case, looks like the only critical point that we have is +2, because -2 is not inside the interval. So there's only 3 critical points to test. We'll find the y value at 0, we'll find the y value at 2, we'll find the y value at 4, and we're only going to specify the y values. Absolute max is the highest y value, absolute minimum is the lowest y value. Don't give me x value, don't give me order pair, just give me the y value. Okay, number 3, find the intervals of concavity for the function. So we know anything with dealing with concavity comes from the second derivative function. So make your way down to f double prime, set f double prime equal to 0, create your concavity sign line, test your subintervals. Yes. To test for concavity, plug into the second derivative function. Yeah. So positive second derivative value will indicate concave up, negative will indicate concave down. Okay, any questions? First page. Okay, next page. We're looking at a derivative graph. So let's create our sign lines here. Remember, if you're looking at a derivative graph, your y-axis doesn't represent location anymore. It represents the slope value of your original graph. So to help us remind us of that, we're going to indicate what we're looking at. Anything above the x-axis is where the original graph is going to be experiencing a positive slope. Anything below the x-axis is wherever my original graph is going to be experiencing a negative slope. Anything on the x-axis is where my original graph is experiencing a slope 0. So I like to have us build our slope sign lines because our slope sign lines will kind of give us a picture of, kind of act as a bridge between our derivative and our original function graph. Okay, so what critical points can we place onto our slope sign line? Good. -3, -1. Good. Now we just look to see where is our derivative graph located. If it's above, that's going to indicate where my original graph is going to be rising. Anything below means my original graph is going to be falling. So between -4 and -3, clearly see that's in the negative region here. It is rising, but that's something else. Okay, we'll deal with the concavity later. But right now, just look at the location. It's clearly below the x-axis, so that's going to translate to negative slope. Between -3 and -1, clearly above the x-axis, that's going to translate to a positive slope. Between -1 and 3, below the x-axis, so negative slope. Between 3 and 4, above the x-axis, positive slope. Okay, concavity. The way we pick out concavity is we look at the peaks and valleys of your f prime. Okay, peaks and valleys for f prime will be your points of inflection of your original graph. So -2 and 2. Between -4 and -2, now look at the rise. Okay, so here my slope is moving in a positive direction. That's going to translate to my original graph showing a concave up shape. Between -2 and 2, the fact that my f prime is decreasing, that means my slope is becoming more negative. That's going to translate to my graph showing a concave down. And from 2 to 4, my slope is rising. If my slope of my f prime is rising, that's going to translate to concave up. All of your statements are going to be relatively easy because you just read it off of your sign lines. Yes. Yes, question? That's true. So at 3, so there's two things that College Board will accept. Because there is no change in concavity on either side of 3, there's positive slope. We can say that that entire place is concave up. But I know on my key, I had that. So either way is fine. You can either break it up as a slope 0 and have another set of concavity or a critical point. But it is not a point of inflection. Yeah, so we can, you're right, we can do this, but we can also leave that out, and it would not be incorrect if we left it out.
The screen's concave up, the force concave up. But on the graph, it's It's not concave down.
Remember, this is not f of x, this is f prime. So f prime, don't look at the curvature because this is not, these are referring to the original shape of the graph, not the shape of f prime. Yeah. Okay, so intervals decreasing. So we have -4 to -3. We also have -1 to 3. And our reasoning is because f prime is less than 0, concave down from -2 to 2, because f double prime is less than 0. There's a relative maximum at x equals 1. Sorry, -1. Because f prime changes from positive to negative. And there's a point of inflection at -2 and 2 because f double prime changes. So this is the way I want you to sketch your graph. Okay, we're going to sketch a graph of f of x, but let's do it in two stages. Otherwise, it feels too much to try to do the slope and the curvature all at once. So we're going to do two drafts here. So the first draft is just looking at your sign line. And there's some specifics here to tell you the range is from -7 to 3. We can adjust that later. Okay, that just means the highest and lowest points. Yeah, there is a target. There is an anchor point here at -4, 3. So we can start there. I'm going to use pencil here because I know that this is not going to be my final draft. But I just want to kind of get the shape going based off of what I see here. So I know, what do you expect at -3? Somewhat relative minimum. And then the graph is going to rise to some relative max. It's going to fall to some relative minimum at 3, and it's going to rise again. So I'm just going to have the shape going. I know that my point may not be exactly where I need it to be, but let's just do this in a couple of stages here. I know that this is not quite right, but at least I have my shape down. I just have to maybe push and pull on the graph to make it where it needs to be. But at least I have the shape down, right? Relative decreasing to relative min, increasing to relative max, decreasing to relative min, increase to relative max. Okay. It should not look like your f prime graph. If you end up copying your f prime graph, or if you end up looking at your f prime graph, you're going to start copying it, and it's going to start looking the same. So base it off of your sign line. Okay, so you're going to cover up your derivative graph. You're just relying on this to build your shape or your movement. Now, it says my range is from -7 to 3. So that means I need my graph to be as low as -7 and as high as 3. So I should not have this hill as high as I make it. So I need to have my hill be a little bit lower to be at 3. And this needs to be all the way down where? -7, right? So I'm just going to adjust it. And if you have different versions on top of each other, that's fine. Maybe you start off using pencil or very lightly, and then from there you push and pull on the graph until it fits where it needs to be. So now that I have my slope, I'm going to go and give it the curvature or exaggerate the curvature in each interval. So I know that there's a point of inflection at -2. So wherever the graph lands at -2, go ahead and highlight that point. Wherever the graph lands at 2, go ahead and highlight that point. You don't have to, it doesn't be very specific, but because you know that these are just points that is going to fall along the path of the graph. You don't have to put a graph X, well, you can, but you don't have to. And now that you have your points of inflection labeled, now we just want to go through and give it the curvature of each of the intervals here, just to kind of over-exaggerate the intervals here. So we have concave up to begin with. Okay, so that makes sense. From -2 to 2 is going to go to concave down. So there's my concave down. And then finally, from 2 to 4, the rest is going to be showing concave up. Okay, next up, I want to draw a sketch an F double prime graph. The location doesn't matter as long as it fulfills those conditions. And remember, your F double prime graph has a different definition for the y-axis. Right? Y-axis now represents concavity, not location, not slope. So to help remind us of that, anything above is concave up, anything below is concave down. Anything on the x-axis is your point of inflection. So go ahead and start off with your x-intercepts, -2, 2 are the only places we need. I guess, yeah, technically 3, since that is a place where the slope of my f prime is 0. And now we're just threading our graph between these points, and don't look at the shape. The shape has nothing to do with this shape is for the original graph. Right now, it's just have to figure out where the graph lands. Is it gonna, this just means above the x-axis, this just means below the x-axis. So we're gonna start off above the x-axis. Then between -2 and 2, it's gonna be below the x-axis. Between 2 and 3, above the x-axis, and then from 3 on, also above the x-axis. Going to bounce off and continue going up. Okay, next up, number 5, use the second derivative test. Remember, second derivative test does not test for concavity. It does the same thing as the first derivative test. So here are the steps that we're going to take. For a second derivative test, you're going to first find your critical points from f prime. So we're going to start off the same way as first derivative test. You're going to find their candidates the same way as first derivative test. You're going to set f prime equal to 0, but after that, you're not going to put into your sign line. You're going to put it into your second derivative function. So now you're going to plug your critical points into f double prime. And after that, you're just going to look at that number and just consider, was it positive or negative? Because if it's positive, you know it's concave up. If it's concave up, you know that your graph must be part of a relative minimum. If your second derivative is giving you a negative value, then you know that's part of a concave down graph, because concave down is second derivative negative, which means relative max. So we're going to use the second derivative to help us decide our relative max, relative min. We're not going to rely on the slope sign line. Okay, so here's f prime. 2 cosine becomes -2 sine. Negative x becomes -1. We set f prime equal to 0. So we're sine negative. We know sine is negative in the third and fourth quadrant. 1/2 sine is equal to 1/2 in that pi over 3 family. Sorry, 1/2 is pi over 6 family. So 7 pi over 6 and 11 pi over 6. Now, normally we would place this on a sine line because we know that we just want to look at the slopes on either side, but we want to do the second derivative test. So we want to insert this into the f double prime function. So this is why it's called the second derivative test, because we're using the second derivative to determine if these critical points are relative max or relative min. Sine becomes cosine. -1 goes to 0. So we just insert 7 pi over 6 and 11 pi over 6 directly into x. Cosine is going to be a negative in the third quadrant. It's going to be -√3/2. But really, the number doesn't matter, right? The fact is that this is going to be positive. Therefore, what can we conclude? If my second derivative is positive, that means my graph is what? Concave up. This is what concave up looks like. What can I conclude? A slope 0 and concave up paired together is going to give me what? Relative min. Yeah. Meanwhile, if I plug 11 pi over 6 into the second derivative, I'll get negative times positive, which is negative. Negative would mean concave down. Concave down would be a relative maximum. Okay, page 3. The graph of f is shown below, which of the following could be the graph of f prime. So okay, I'm going to highlight this point and call it C here, because I want to create a slope sine line just so I can kind of get a picture as to what I can expect. I know I'm going to call C my relative max. And I know my graph is showing exactly this, right? Positive slope followed by negative slope. This is the shape of my original graph. And if I had to guess, there is points of inflection here. So I'll call this point D, and point E, right? You can kind of tell that it starts off concave up. At some point, it's going to turn to concave down, and then it's going to turn back to concave up. So I have some information about my concavity as well. It starts off concave up, shifts to concave down, and back to concave up. Now, if I want to create my F prime graph, I know my F prime graph is going to have this behavior. I know that point C is where my slope is 0. So point C will have to be on the x-axis. So the graph is going to start off above and it's going to end up below. So it's going to be something like this, right? Start up above and then ends up below. There's more to it than that, but I know at least it needs to start off here and it ends here. Next up, I can also give myself slope here. I know that on my F prime graph, concave up means positive slope. Points of inflection is D and E, which means that these will be the peaks and valleys of my F prime graph, right? So I'm going to call this point D, and I'll call this point E. So I know there must be a relative max here, and I know there must be a relative min here. So I just want to kind of reshape my graph until it fits that criteria. It's above and below where it needs to be, but also is showing concave up, positive slope. It's a relative max, concave down, negative slope, relative min, concave up. So this fits best with answer choice A. And now number 7 is the other way around, where the f or the derivative of g is shown. This is my g prime, and now I'm looking for the g function. So let's shift gears here. This is now my derivative graph. So my derivative graph is telling me information about the slope, not giving me information about location here. And I know that these will be slope 0, so I'll call this point C and D. And I know that the peaks and valleys is going to be my point of inflection, right, of my original graph. So here's my sign line. Slope is going to be 0 at C and D. I'll just call this C and D. To the left, negative slope. To the right, positive slope. To the left of that, negative slope. I'm expecting a point of inflection at E. Concave up, concave down. So I need my graph to be shaped like this, where I'm expecting a relative min at C. I'm expecting a relative max at D. So I'm just going to sketch my graph without looking at my choices here. So at C and D, I'm expecting a relative min, followed by a relative max at D. And at some point in between, it's a point of inflection. So I want my graph to maybe look something like this. All right, relative min at C, relative max at D, and point of inflection at E. Let me see what graph has this basic shape. Like location doesn't matter, it's the shape that I'm after. And the graph that resembles the shape most is B. Okay, we'll stop there. We'll continue with our quiz review tomorrow. No homework tonight. We'll pick up tomorrow. Is that let's say? I'm sorry. There's my bad. 1 through 13. Sorry. I didn't look at the calendar. Just AP practice.
1 through 13. Oh, yeah, you want to check that.
Yeah.
That's. Oh, no.
No homework tomorrow.
Oh, the quiz is on Monday?
Quiz is Monday. Quiz is Monday.
I thought it.
I can meet your phones.
You know how on other tests we have like, or like quizzes or tests, we have to like up that with online.
Yeah, I'll
There one.
yeah, I'll give that to you. Yeah, I'll find that and give that to you.
Yeah.
Go ahead.
You can't do it really.
I don't trust you like that.
Thursday, but I have a